Actually, yeah. So one thing I want to make
Well, let's get started. Okay, today is the last regular quantum materials and device seminar this term, particularly for the ES-294 people who will be looking for your last signature at the end of the class. Please do that. We will have two special quantum materials and devices seminars in May. Mike Cromie will be here on May 16th, and he's one of the leading people who use cooled scanning tunneling microscope to actually understand how graphene and other materials work. And then Qikeng Shui will be coming from Tsinghua University on May 15th, and he's really one of the leaders in the growth of topological materials, and he'll be telling us about some of his most recent work. So these are two great talks, and we have them because we managed to get the people in town, and we thought we might as well benefit. Today we have, speaking of topological materials, we have Joel Moore, who's a theorist who dreams things up in this field. I'm an experimentalist, and I always think the experimentalists discover it first, and then the theorist tells us how things actually work. But in this field, it really came out of theory. And it turns out you can make a whole new class of materials with properties, edge states going around the outside, resistance about data corruption, and the like. There's a whole new world of possibilities, and it's been very exciting with even new types of materials that Nick will be telling us about today. So I look forward to hearing that.
Thank you. So I'm very happy to give a talk here. It was only today that I learned that this is technically a course where many of you have to be here. There are some of you here who are experts, and I hope I have something to say for them, and I also hope that some of it is accessible. But either way, please interrupt me en route, whether something is too fancy or not fancy enough, and I'll try to give some more details. So I have a brief introduction to the general area of topological phases, at least one big category of topological phases, and how those relate to other things in solid-state physics. And then I'll focus on some new stuff, which actually connects to various experiments in this center as well. And that's basically trying to take some of the magic of topological states. This word topological will be defined soon. We've mostly thought about topological states as being insulating. That's not entirely true, but at least most of the quantized responses and so on, the magic that you can measure has been in insulating states. But now we find new kinds of topological materials that are actually semimetals. And it's natural to ask, well, what might be interesting in those? And I'm going to try to argue, basically because we thought about other things and couldn't make them that interesting. And then we thought about optics, and it wound up being surprisingly interesting that optical responses are very exciting in topological semimetals. So that's about 80% of the talk, and I'll mention some works later on, but this was done with a lot of people at Berkeley. The last bit of the talk I wanted to talk about here because it's very similar in spirit to a lot of the experimental work that's gone on in this center over the years, which is about imaging electron flows, electron currents, and so on. So for a slightly different problem, there's been a lot of recent progress in the community that works on this kind of thing, where there's a version of hydrodynamics that is exact and solvable in some many-particle quantum low-dimensional systems. And what that means, I'll try to sketch, and then if you like it, you can look up the papers, which are quite recent, and if you don't like it, it'll only be 20% of the talk. So the quick outline, there are various ways to understand topological phases, and I'll talk about one that I like, which is based on the idea of a Berry phase. And the good thing about that is it doesn't just explain some kinds of topological phases. It certainly doesn't explain all topological phases, like you might have heard from Leon about Majorana's and things like that. So those are not as directly connected to what I'm talking about. But in addition to explaining some topological phases, and maybe the easiest ones to make in the lab and measure, it also explains a whole bunch of important properties of solids that are not exactly quantized, but still interesting. In fact, a lot of basic questions about solids we didn't know the answer to until this Berry phase concept. So once we have a topological phase, it's natural to ask, what can we measure in it? You know, we'd like it to do something interesting, often electromagnetic. So this is maybe the motivating question for the talk. And the new stuff is on topological semimetals. So I'll give one example of a nice electromagnetic response in topological insulators and related materials, which goes back to about 2010. But then the new stuff in the last couple of years, and these are the references, are about topological semimetals, so-called Weil and Dirac semimetals. And these are three-dimensional materials that have effectively massless electrons on some level. They're kind of like three-dimensional versions of graphene, if you've heard about that. And there's been quite a lot of discussion in the community about what are their unique electromagnetic responses. And we have almost a negative answer for standard linear responses, which is that there's nothing particularly specific to Weil or Dirac semimetals. But when you go to nonlinear effects, there are some very interesting things that happen. And this actually connects to some measurements that were done recently. So no one has seen exactly the effect that I am going to focus on, which was just posted in November. But there are some related experiments. So one is by Joe Ornstein's group at Berkeley, which is on second harmonic generation in tantalum arsenide. There's an experiment on the effect I'm going to talk about, which I saw much of the data only today, which is something called circular photogalvanic effect. So you'll hear what that is later. But there's an experiment by Nugedik's group at MIT, and then there was theory related to that experiment by a Caltech and MIT collaboration. And then finally this hydrodynamic stuff. So as background, I'm going to try to sketch what is the Berry phase, and then come back to this list. So this is kind of where we're going. The point is, if you can follow my next couple of slides, which will define some objects that are like a vector potential and like a field strength, but live in momentum space, every simple thing we can make out of these quantities turns out to have a physical meaning. So in other words, if you can understand the Berry phase, which admittedly is not that easy in 5 or 10 minutes, but maybe you'll be motivated, then you will understand, first of all, the quantum Hall effect, then topological phases that depend on symmetry, and examples of those are these so-called topological insulators. Electrical polarization is not always a quantized thing, but it also depends on the same sort of geometrical quantities, the Berry phase. The magnetoelectric effect is one that I'll talk about in a little bit of detail, and then I'll finish up by talking about metals. So let me get started on this, and maybe I'll try to add a little bit of introduction as I go along to say what is the Berry phase, and then give a couple of examples. So, and here, this will be a little bit brief because I think you've probably heard other people talk about topological phases before, but maybe not exactly in terms of these concepts. So, with the Berry phase, the thing to remember is that when you took undergraduate quantum mechanics, there were several lies you were told, at least if you took it at Berkeley. Or maybe they were half true. So something that you were told that is true, but only part of the story is the so-called Adiabatic Theorem, which is like a quick way to solve problems. So if you have a Hamiltonian that is slowly changing, and you're in a non-degenerate eigenstate, then you basically stay there to very good accuracy. So that's true, but it's part of the story. You might think about your Hamiltonian as a function of some knobs in the laboratory, some parameters. So suppose you change those parameters, that's how you change the Hamiltonian in time. You twiddle your knobs, and you take the Hamiltonian around a closed path in parameter space. If you do that, you can make a quantity called the Berry phase, which is an integral over parameter space, and I'm jumping ahead a bit. My parameters are just going to be momentum, and I'm going to make this object out of the electronic wave functions. And in the cases I use it, it doesn't have much to do with adiabatic evolution. What I'm describing here is probably the simplest example and the one that Berry presented to kind of unify a bunch of different problems that people had talked about before. But let me just tell you how you make this object and then try to convince you that it might be physical. The idea is, so I've got a single non-degenerate state at each point in parameter space. Let me call that psi k. And then I make this object, which depends on how is the wave function changing as I change the parameters. That's what this derivative means. So it's like a vector, because this is a vector with as many components as there are parameters. So it's like a vector in parameter space. And I'm writing it the same way that we write the vector potential in electromagnetism. So this is the same A, or at least the same notation for the thing whose curl would be magnetic field. So why did I write it like that? And then to get a number, a phase, I just integrate that over the loop. So why did I write it this way? And does it depend on choice of reference wave functions? And those two questions are related, and let me explain what that means. The idea is that suppose I form this object, then if you made a change in the wave function, then this object, which can only be a phase in the non-degenerate case, then this object would change by a gradient of the phase. And that is just like the vector potential changes in E and M. So in other words, this is gauge dependent, we say, which just means if I change the phase of the reference wave functions, I might get a slightly different vector potential than you will get. So A itself at one point in parameter space is not actually physical or measurable, but its curl is, because curl of a gradient is 0. So that's saying, and you can work through the math yourself if you don't trust me, that if you take this object, if you take some wave functions, and I'm going to focus on wave functions in a solid now. If you take the wave functions in a crystal, and I form this object, then I can make things out of it that at least are well-defined and might be physically meaningful. And the first example of this being physically meaningful was actually part of what won the Nobel Prize this year for, at least the Thales and Haldane piece of the Nobel Prize was related to the following observation. So this object, and this is where the topology starts to come in, this we think of as like a curvature. We call it the Berry curvature. So it's something made from the wave functions, and it's gauge invariant, unlike A. If I integrate that over the entire Brillouin zone, integrals of curvature are sometimes quantized. That's the way topology works. So this is like a curvature of wave functions. The total curvature of wave functions is quantized. It's called Chern number or TKNN integer. And when I do that integral, I always get an integer in the right units. So that's kind of a topological curiosity so far. It says that every time I give you a two-dimensional band, then I can give you an integer, which is like a winding number, topological invariant of that band. And the second line is the magic, and it's pretty concise. What they showed in this paper, starting from the standard Kubo formula for electrical conductivity and doing some manipulation, is that what that integer means is that if I fill up that band with electrons, that's how much it contributes to the quantum Hall effect. So I sum over all the occupied bands, these magic numbers, and that tells me the integer quantum Hall effect. So that's the first example of a topological phase, was the integer quantum Hall effect. And I'm not giving my normal colloquium 15-minute introduction to topological phases, but you can learn more about the integer quantum Hall effect if you like. Let me give you an example that's let me step up a little bit in sophistication where learning something about topological phases actually teaches you something even about old-fashioned effects in older materials, and then we'll move on to the new stuff. So a three-dimensional topological insulator, as was mentioned a bit in the introduction, is a new phase that was discovered, well, I guess it was predicted by theorists starting around 2005 and then discovered by experimentalists quite soon after. And basically it's an insulator where however you cut it, there's always an atomically thin metallic surface. And that was seen in photo emission, and you could count that as the discovery of the phase. But that's not totally satisfactory because, at least at first glance, there wasn't anything quantized like there is in the quantum Hall effect. We'd like to know something we can measure that has a unique value, at least that would be nice. And it turns out that the answer was sort of indirectly given by particle physicists back in the 1980s. So the way it works, and the way maybe electromagnetic responses, you already know some, and I'm going to tell you about a couple of others, but if I go into an insulator, the laws of nature change in various ways. So one is simple. The dielectric constant changes, the permeability changes, whatever. A slightly deeper one is that we've known for a long time, since the 1950s, that if you go into some solids, it's like there are terms that are linear in electric field and linear in magnetic field. And it was thought, I think until the 1980s, that the only way you could make terms like this appear, so these are terms that you add to electromagnetism, and I'll tell you what they describe in a second, but basically we thought that terms like this could only exist in special materials that had low symmetry. They had to break inversion, and they also had to break time reversal. They had to break inversion because it's linear in E, and they had to break time reversal because it's linear in B, and these were so-called magnetoelectric materials, which is connected but not exactly the same to multiferroic materials. You've heard of that. What this means is very simple. It means you have a material where if you apply an electric field, it becomes magnetic. It generates a magnetic moment. And if you apply a magnetic field, it generates an electrical polarization. So that magnetoelectric effect was measured for many years and not actually fully understood until topological insulators were discovered. I'm going to try to claim. So anyway, this term was believed to exist, but only if you broke symmetries. And then Wilczek pointed out that actually, if you have time reversal symmetry, something very special happens. And they did this before there were materials or anything. It was just noticing an interesting mathematical property. And I'm going to give you the condensed matter version of what he did. So first of all, if you make this dimensionless in the right units, you've got a parameter in front which is called theta, which is indeed the same thing as the so-called theta angle in particle physics, which is why he was thinking about it. But for now, suppose this is some dimensionless parameter. Normally, the way all those symmetries, what that means is that theta would go to minus theta under the action of time reversal, say, and you say, well, the only value that's equal to itself is 0. So the point of Wilczek's 1980s paper, is basically in one sentence, is that theta is actually an angle. And if you have an angle that's equal to minus itself, then things get interesting, because there are two possibilities. Theta could be 0, or theta could be pi, or 180 degrees if you prefer, because pi is the same angle as minus pi. So Wilczek's claim, which maybe sounded bizarre, was that there are exactly two kinds of insulators that have time reversal invariance. There's the theta equal to 0 kind and the theta equal to pi kind. And if you have a boundary between them, for example, if you go from a theta equal to pi insulator to vacuum, then there should be some kind of special boundary. Well, now we realize that's true. If you want theta equal to 0 are the ordinary insulators and theta equal to pi are the topological insulators. And I want to explain briefly, to try to make this seem less crazy, that this definition is actually connected to, first of all, things we knew about topological insulators from the other picture, which is that they have special metallic surface states, and second, to measurements on graphene actually done by Philip Kim when he was at Columbia. So here's why this term is special. So from the symmetry point of view that I've said so far, I might as well have written E cross B or something else, but why did I write E dot B? Well, E dot B is a little bit special by sort of undergraduate calculus, which is that this is a total derivative. It's a total derivative of ADA, which is sometimes called electromagnetic Chern-Simons. Basically, the fact that it's a total derivative of something means you should think of it as maybe being a boundary effect. And if you ask what boundary effect is it, it's the following. To say that a material has an E dot B term in bulk actually has a simpler interpretation. It means that if I go from this to theta equal to 0, say in vacuum, let's define vacuum as theta equal to 0, then there's actually a Hall effect. Hall effect means current flows perpendicular to electric field at the boundaries. So what theta means in condensed matter language is the following. If I say that I've got a material which has a value of theta in the bulk, then that means that its surfaces, if I can gap the surfaces, something odd happens. The surfaces don't have integer Hall effect, they have an offset. For theta equal to pi, they have half integer Hall effect. So the way the Hall effect at the surfaces connects to what I told you about E dot B is the following. If I apply electric field, Hall effect at the surfaces means the currents run around like I've drawn, that produces a magnetic field, vice versa, but that's harder to draw. So this is saying that if you have Hall effect at the surfaces, you do get the magnetoelectric effect I talked about a moment ago. So where things get a little tricky, for this all to hang together, it must be that the topological insulator surface state, which was discovered in photoemission and known to be like 1/4 of graphene, in a sense I'll tell you in a second, that must be something that if I could put it in a quantum Hall state, would not have an integer quantum Hall state, it would have a half integer quantum Hall state. And indeed, we think that's what happens, because graphene has 4 Dirac cones, if I include the 2 points in the Brillouin zone where they happen, and a factor of 2 from spin. Topological insulator surface, in the simplest case, has 1 Dirac cone. If you measure the integer quantum Hall effect in graphene with 4 Dirac cones, you see a funny pattern. And this is the data I mentioned from Philip's group. So these are Hall plateaus, and if you look at the values, these are like -10, -6, -2, 2, 6, 10. That's very different from gallium arsenide, say, where you'd see 0, 1, 2, 3, 4, etc. What's special about these numbers, the Hall plateaus in graphene are 4 times the half integers, which means if you had something that was 1/4 of graphene, which is what we think the funny surface state of this material is, you should see half integer Hall effect, which is equivalent to theta equals to pi. So this is all just maybe the most recent example of the long-standing trend, which is that there's a lot of stuff in insulators that is governed by the Berry phase in kind of interesting response. And if you want, I have only 2 mathematically sophisticated equations in the first part of this talk, and I deleted the first one. So this is equation 2 in green, and green means a little subtle, so you might have to think about what it means for a few minutes. It took us about 2 years, but you can probably do it more quickly. So the idea is that the orbital magnetoelectric effect that I can measure is connected to theta. And the way I can compute this microscopically, it actually comes from the same Berry phase I talked about before, except it's the non-abelian Berry phase. It depends on having multiple bands occupied, and this is something that appears in particle physics quite a lot. It's the non-abelian Chern-Simons form. So some fancy integral over the Berry phase will actually tell me what theta is. And another way to put it is that the magnetoelectric effect, which was measured for 50 years, we didn't know this formula, which means we didn't know how to calculate it until recently. So that was my lightning review, and let me go back quickly to my historical chart of parts 1 through 3. So I tried to sketch very quickly. I didn't really do number 2 in the interest of time, but by calculating the Berry phase for filled bands, I can understand the quantum Hall effect. If I calculate the Berry phase with time reversal symmetry, I find that there are only 2 values, and those correspond to ordinary and topological insulators with time reversal symmetry. So again, the Berry phase is a good, detective. Electrical polarization I'll tell you about in a second, because that's actually the easiest way to get into thinking about metals. And then the magnetoelectric effect, that's fairly recent, and it took, as I said, several years for the community to kind of converge, but it's really the answer to what's quantized in topological insulators, and it turned out to have a nice spin-off for ordinary magnetoelectrics as well. So now let me go back to something simpler and tell you, how do you picture what this Berry phase means in terms of quantities and solids that you're actually used to thinking about? And then I'll tell you what's the biggest mistake in Ashcroft and Mermin. I was talking with Professor Halperin earlier, and we both mentioned we both still use Ashcroft and Mermin. Apparently, he told me it costs something like $400 now, which is unfortunate. It's a great old book, but there are ways in which it's incomplete, and I'll tell you what. So, to calculate electrical polarization. So electrical polarization, was known to the ancients. It's just the idea that some materials have a preferred direction. You can think of them as having an electric dipole moment along that direction. It's a little bit subtle because you measure it by measuring surface charge, and maybe that depends a bit on how you prepare the surface and so on, but the idea that some materials have a dipole moment is not new. The way you calculate that, given just the unit cell, was worked out by Fowlis and Kingsmith and Vanderbilt, and it's actually just the integral of A. So this is even simpler than F. It's the integral of A, and if you're worried from what I told you before that A could not be gauge invariant, it turns out that if you make a loop integral over the whole Brillouin zone, it is actually just gauge invariant enough to correspond to polarization. So what that means, the way to think about what the Berry phase is telling me, is that it's something about where is the electron sitting in the unit cell. So that's kind of intuitive and a little bit sloppy. So if you want a more precise way to think about the Berry phase is connected to something about where the electron sits, then the way that you actually derive this formula is you show that if you change the polarization, then charge moves around. It moves in the unit cell. So changes in polarization are like currents. So some charge is moving around, and that's maybe an argument that the Berry phase has to be connected to spatial motion. And that is going to be the correction, at least the first correction I would make to Ashcroft and Mermin. I'll tell you in a second how it comes up in the semi-classical behavior of metals. So polarization is not always quantized. It's not usually quantized unless you have symmetry, but it's an observable that is controlled by the integral of A. So if you want a simpler or more general reason for why things like polarization had to be controlled by something like the Berry phase, something that comes out of the wave functions at least, if you have time reversal symmetry but you break inversion, think about the band structure. Think about E of K. So as you know, the first semester you take in solids is almost all about band structure, which is nice. It tells you the difference between metals and insulators and so on. But E of K can't tell you everything, because if you have time reversal, then E of K is automatically equal to E of minus K, even if your crystal broke inversion. Which means that if you want E of K is too symmetric to tell you some things, so most of the things that come out of inversion breaking don't come from the band structure, they come from the wave functions, and at low energy, usually, in the previous version of this talk, I would say at low energy they come from the Berry phase, but now the hero of the middle part of this talk is something else, something that we should add to the Berry phase in our list of important low energy ingredients in solids. All right, so this is the term that is not there, but was actually discussed before Ashcroft and Mermin, which I think is from 77 or so, by Karplus and Luttinger, and no one really understood, I think, very convincingly what they were talking about, at least maybe Ashcroft and Mermin, but I think the field in general was skeptical until it was realized that this is actually a Berry phase, and it's very much connected to that polarization idea. So what this equation is about is the easiest way by far to do a calculation in a metal is to think about wave packets, something classical. We all know what a wave packet is. So wave packet, the first part that's the group velocity. That says that because band structure is different from in free space, there's a different velocity. The second part, well, F, this is the same Berry curvature I talked about before, but you should think of it as dA by dK times dK by dt. So it's like the total derivative of A, which is the total derivative of polarization, which is indeed a current. So the way to think about this term is that it's the anomalous velocity. It's the extra part of the velocity because the electron is moving in the unit cell. So suppose that at one value of momentum, the electron is on atom A. At another value of momentum, the electron is on atom B. If the momentum is changing, which is dk dt, then the electron moved from atom A to atom B, which is an extra part of the velocity that you wouldn't get here because this is the group velocity of a point particle. So there's an extra piece of the velocity, and Karpos and Luttinger were thinking about it because it seemed to maybe explain part of the anomalous Hall effect in magnetic metals like iron, something that Hall measured, I think, back around 1890 or so. I'm going to talk about metals, which are examples 2 and 3. But first, let me tell you the way that we thought Berry phases would work in metals and why they wouldn't be quantized and they wouldn't necessarily be super exciting in metals, at least to me. So the anomalous Hall effect is a very old and surprisingly difficult problem. I think the state of the art is still this nice review article. There are at least a couple of experts in the audience I know who may know more recent work than I do, but there's a nice review from 2011, and you can tell that it's a tough field because even in figure 47, it's still a speculative and schematic phase diagram as a function of how clean the material is, basically, the diagonal conductivity and the temperature. And the reason why it's kind of a hard problem, the Berry phase, the geometric stuff that's nice appears in this middle region, which is not too clean. If it's too clean, you're dominated by Fermi surface behavior. If it's too dirty, you're dominated by localization physics. In between, you're maybe dominated by this term. And the idea of this term is that you just take the same integral that would be the quantum Hall effect, but instead of doing it over the whole Brillouin zone, you only do it over the Fermi sea. And there are other ways to write this term, but this is maybe the simplest. So that says that, okay, if you make a metal instead of an insulator, maybe part of the metal's conduction is governed by the same thing that you had in an insulator, but now it's not quantized. So that is probably true and important, but not very topological or quantized or anything. So I'm going to talk about 2 other Berry phase effects, and one is kind of simple to draw, and it's maybe the simplest effect that you could invent to try to explain consequences of this term. So remember, this term is saying that if the electron has a spatial location that's changing with k, and if k is changing with time, then there's an extra velocity. And now's where light starts to become the hero of the story. So there's a nonlinear optical effect that we thought was a very good measurement of the Berry phase, even in kind of simple semi-classical physics. And this is this circular photogalvanic effect, which is also called the nonlinear Hall effect, I think by Liang and Soderman. So the circular photogalvanic effect is the following. If I put on circularly polarized light, there can be a photocurrent. Photocurrent means current proportional to intensity of the light, so that's nonlinear because intensity is E squared. And the idea of the circular photogalvanic effect is that sometimes you have a current that goes one way for right circular light and the other way for left circular light. And there's many years of experiments on this by a group in Regensburg led by Ganichev and so on. And to their credit, they had an interpretation for many years based on spin-orbit coupling, and then they did it in silicon and they saw the same effect that they saw in gallium arsenide, which basically proved that it wasn't spin-orbit coupling and it wasn't quite clear what it was. And then the point of all this stuff was to argue that it's a Berry phase effect and it's very simple. And the idea of the Berry phase effect here is the following. If I'm doing low frequency light, so these are terahertz experiments, and I think about just semi-classical electron transport, when the force on the electrons is pointing to the right, the electron distribution, which is the gray circle, gets displaced a little bit from the ground state. If I've got right circular light, say, the gray circle goes around like that as the light polarization goes around. And if you do a quick calculation, you realize that the ordinary velocity, which is along the electric field, averages to 0 by the time I get around. Think about the anomalous velocity if the material breaks inversion. So basically, here, when I'm displaced to the right side, I've got a small non-zero average of Berry curvature because of the inversion breaking, and dk dt is down. When I go the other way, by the time I've gotten around, dk dt is now up, and I've also flipped the average of the Berry curvature because I've passed from k to minus k. So that's all just trying to argue in words that in this equation for the velocity, this term averages to 0 and this term doesn't. And this term comes from F, which is the Berry phase. So we were interested in this basically as a way to pull out the Berry phase. Turns out that it's more complicated and interesting when you go to non-zero frequency, which we didn't know in 2010. But first, let me explain something that wound up being about wild semimetals, even though we had no idea we were actually working on wild semimetals. We thought we were trying to resolve something about high-temperature superconductors. That just shows, I guess, that we didn't know what we were doing, but it was still useful. So I would now talk about a linear optical property, because we might think those are simpler. So there's a particular linear property that we were interested in because of some well-known experiments on superconductors from Stanford that I'll tell you about just for your general education. Other people were interested in something that they thought was a different measurement in wild semimetals. So the basic fact is that if you take some sugars or if you take some low symmetry crystals like quartz, then when light passes through, the polarization direction of the light rotates. It's like a Faraday effect, except the material doesn't have to be magnetic if the material is, in a sense, chiral. So we were interested in that, and I'll show you the experimental data that got us interested. But basically, we did a calculation of this in some detail to try to figure out how our earlier theory was consistent with a requirement from a classic paper by Bert Halperin. And I'll tell you about that just as background. I won't go through our calculation. But then what we kind of realized in the process of doing that is that this problem is actually the same problem. And now is when I start saying things that might be slightly controversial, but hopefully no one in the room minds. And if they're on the internet watching on YouTube, that's okay. The problem we were doing, which is optical rotation, is exactly the same thing as the chiral magnetic effect proposed in wild semimetals, although most of the time the effect that people originally thought was there is zero. Sometimes it's non-zero, but even when it's non-zero, this is a horrible name. So let me try to convince you of those things gradually. So first, why did we care? So what is this optical rotation, optical gyrotropy, natural optical activity? Those are all names for the same thing. It means you take a non-magnetic but low symmetry material and you pass light through, and the plane of polarization of the light gets rotated by a little bit. And you can imagine that happening if you had a material that was like a helix or kind of chiral, which it turns out the low temperature phase of quartz is. Selenium will also do the trick. You get this effect, and it's slightly useful for various things. It led to a lot of the understanding of symmetry in crystals, actually, understanding optical activity. And now, going to much more complicated materials, this is the phase diagram of the cuprates, and surprisingly little has changed in this phase diagram since I was a graduate student, but one big change is this area in red, which is that it looks like there's a region where some kind of charge order onsets, and there's an optical experiment that sees something happening in the same place, but what it sees is inconsistent, or at least different from what all the other measurements see. So that I want to explain, and that's still a puzzle actually, but at least it's good for you to know about, that not everything is done, even with the cuprates. So the basic idea was that, and Eugene has actually worked on possible explanations of this charge order as well, so he knows more about the charge order than I do definitely, but let me mention one puzzling experiment. So what's seen here looks like the following. It basically looks like you're going from the symmetry of a square to the symmetry of a rectangle. It's like the material is distorted along one axis, say, in symmetry terms. But there's one other experiment, and I'm going to explain why you can't view it that way, which is the onset of the Kerr effect. So Kerr effect is like the Faraday effect, except you're bouncing light off of something instead of passing light through. It's the reflection version of the Kerr effect. The Kerr effect is in transmission. Sorry, the Kerr effect is the reflection version. The Faraday effect is the transmission version. So something onset here, and for a while, the reason why we got interested in the problem is that there was an effort from some theorists to try to say maybe these are all coming from the same thing. But here's the story. So what's measured at Stanford is bounce light off, measure the polarization rotating. The basic idea, and the consistency check that we had to do in our theory, and this is the result that goes back to Halperin, is that there's a big difference between magnetic materials and non-magnetic materials, which is that if you want, they can both have rotation of polarization and transmission. You can have a Faraday effect in a magnetic material, and you can have optical activity in a non-magnetic material, and they basically look the same. When you reflect, you only get an effect if you have time reversal braiding. So this Kerr effect is only there in magnetic materials. It's actually not that simple to prove that. There are claims of simple proofs in recent years that I don't think are actually good. I think there's a reason why the original proof is fairly long. That's maybe a side topic. But basically, this is the controversy or the story that's still out there that I hope someone will figure out the answer to, which is, All the other experiments are explained by charge order that goes from a square to a rectangle. That should not appear. If the Stanford measurement is doing what it's supposed to do, that shouldn't appear. And the point is that the only thing, unless the Stanford experiment is constructed badly, but it passes all the tests it should pass, a linear response cursing on normal incidence has to involve time reversal breaking. I mean, they may not have checked its linear response and things like that, as far as I know, but at least the most logical explanation is that there's time reversal breaking. It's seen in multiple materials and so on, but that is still a puzzle. So why this happens? Does it mean there's time reversal breaking? Why does it onset at the same time as charge order, etc.? Maybe those are puzzles for another day. But now, so we were working on that problem of optical activity. Other people were working on these new topological semimetals. We were kind of dabbling in that as well, but we didn't connect it to our optical activity work. So I'm going to tell you a little bit about this big discovery in the last couple of years of three-dimensional Dirac and Weil topological semimetals, and then explain how it's connected to what I just told you, even though at first glance there's no connection at all. So a challenge that goes back to the 1930s in the theory community is, can you make three-dimensional linear band crossings and put the Fermi level at one of those? So can you make a material whose low energy electrons are three-dimensional fermions? And they're basically two kinds of, well, if I don't make Majoranas, if I don't get rid of particle number conservation, then I've got two kinds of three-dimensional massless electrons. They're basically two different ways to go from graphene in 2D up to some 3D material. If you have both inversion symmetry and time reversal symmetry, you get the Dirac equation, which is a 4x4 matrix that Dirac wrote down. In our condensed matter language, these are semimetals where four bands come together, and those were found starting in 2013. Very soon after Dirac, Weil pointed out the following, that if you have massless particles, which we're talking about here, linear dispersion, so Weil was thinking about particles back in the old days, and he said, well, if you've got a massless particle, it can have a fixed helicity. In other words, you could have a neutrino, say, that is massless and always left-handed. And for a long time, we thought neutrinos might be like that, until neutrinos were found to be massive. If you've got a massive particle, then you can change its helicity by changing reference frames, basically by catching up with it. So it seems at the moment like Weil particles, which would be 2x2 matrices, because you basically separated the Dirac equation into left-handed and right-handed parts, we don't think those exist in the standard model. Neutrinos were the possibility, and they aren't. But they do exist in solid state, so that's nice. We have Weil fermions, and the particle physicists maybe don't. And maybe what I think, at least a big part of what revitalized this field is some recent work that explained how these were discovered. So first, there's kind of a topological interpretation of what's going on in these Weil semimetals, which is that you've got a linear band crossing, and you can show using actually the same Chern number and Berry phase I talked about before, that if you make a little sphere around one of these linear crossings, then you'll get a topological integer, which we call the charge of the Weil point. And that total charge is always even, but otherwise these can be distributed in various places in the Brillouin zone, dependent only by theory. So it's sort of known that there's a topological aspect of Weil semimetals. And then a really important work as far as their experimental discovery was a theoretical paper by Ashwin Vishwanath and collaborators, which showed that if you look at the surface of one of these things, then there should be an unusual Fermi arc at the surface of the material that basically goes between positively and negatively charged Weil points. So there's some kind of unique surface state you can look for. There are many experiments. There are a lot of great discoveries around the same time. I'm not going to try to list all the references. It somehow gets a little contentious occasionally. Anyway, they were found. They do exist. That's my main point. So now we'd like to ask, well, they've got this surface state. That's terrific. What can you do with these materials now that you have them? So this is where, maybe the second point where I say things that are possibly mildly controversial. And this is where that chiral magnetic effect came from. At least, to be precise, there are some papers on the chiral magnetic effect that are correct, but there it's a strongly non-equilibrium effect. Linear response is where I have a problem with it. But where that idea came from was the following. If you take Weil fermions, so people thought about these for 50 years because they hoped they would be in the standard model, and you just asked what's special about them. Maybe the most special thing about these Weil fermions, and you'll see these words in a lot of papers on the archive, is the chiral anomaly. So what's the chiral anomaly? It means that whenever you see anomaly, it means that a symmetry is broken that you would have thought naively was there. So in this case, it's just charge conservation. If you take electric and magnetic fields and you apply them to a system with only one while point, which we already said was impossible to have just one, you'd find that charge was created. If you've got positive and negative while points, you find that basically in the presence of electric and magnetic fields, which is a nonlinear effect because you've got two of them, charge should flow from one positive while point, say, to another negative while point. So that is true, but it's nonlinear, and when you start measuring effects over E dot B, there are a bunch of other effects that come in, so I'm not totally convinced by the existing observations of magneto transport that they have to be connected to the chiral anomaly. But then the idea was, we can make a much easier version of this and look for it, and it sounds a little bizarre, and it's only true in a limited sense, but the idea was that if I took this and I thought about while points at different energies, so going back here, I'm allowed to have these occur at different energies, so there's like a chemical potential between positive and negative while points. A little bit naively, that could replace the electric field, and then you would get something where if you just apply a magnetic field to a material, you would get some kind of current. And it turns out that there's a very subtle reason, well, there's both a high-level reason why this is zero, and the details of how it works out are kind of cute and topological, but it leads you to understanding optical activity at low frequency in a very simple way.
So what is CME?
So CME is chiromagnetic effect, and we have tried to rename that to gyrotropic magnetic effect because it's actually nothing other than optical gyrotropy. So this, let me explain under what conditions this is zero and when it's non-zero, and then when it's non-zero, I'll give you a formula for this alpha tensor. So G is gyrotropic because our point was that what people had previously called the transport or finite frequency limit of the chiromagnetic effect is nothing other than old-fashioned optical rotation, and it's got a pretty simple formula.
Yeah. Well, what do you mean in the line CME idea, the total charge of while points in the crystal and so forth? What do you mean by that?
So the idea was, the reason why the total charge of while points in a crystal is zero is something called Nilsson-Unionia. So there's kind of a topological reason why you couldn't just directly measure the anomaly at one point. You'd find that on average, if you like, the total effect cancels out. So all I mean, the chiromagnetic effect idea was that I could still measure something even under this condition and even without using an electric field. I guess that's all I mean. That even though some of the simpler things I could try to measure are either nonlinear or would cancel if I had multiple while points. So let me give you a simple picture for why you would think this is there. And yeah, now I'm going to kind of look ahead and outline where I'm going and then give a couple of details, but not all that many. So this chiromagnetic effect idea was that you might, under some circumstances, get a current that is just induced by magnetic field, which is related to the chiral anomaly in particle physics and baryon curvature and so on. So at equilibrium, I think everyone now agrees that this is zero, and that's sometimes called Bloch's other theorem, actually. It's the difference between electric and magnetic fields. A system in an electric field doesn't reach equilibrium. A system in a magnetic field can reach macroscopic equilibrium with no macroscopic currents. I don't know I've never managed to find a really good proof of that, but I know microscopically how that works out here. But this is what I'm going to build up to in just a couple of slides. There is a different limit from normal equilibrium, which is what's sometimes called the transport limit or the uniform limit. So if you remember, and this maybe gets to graduate solid state courses and remembering something you might have heard, there's often a difference in the order of limits between whether you take wave vector to zero first or frequency to zero first. For example, with electric fields, one of those gives you electrical compressibility and the other one gives you electrical conductivity, and usually we care a lot more about electrical conductivity, which is the one you get by first taking Q equal to zero and then taking omega goes to zero. So people, once it was realized that this is zero at equilibrium, I'll give you a simple example of how it comes out to be zero. It can be so people got excited, okay, well there's a way to make it non-zero, which is to look at what we normally look at in transport, which is this first Q goes to zero, then omega goes to zero. But you should be a little bit alert when you have a magnetic field in a problem and you're at non-zero omega, because an oscillating magnetic field has to have an electric field along with it. It's basically a light wave. So it's a current induced by a light wave, and that's actually just optical rotation. That's kind of the point of this PRL. And the formula that computes this has nothing really to do with Weyl physics. It's actually a very simple formula. It may not look simple the way I wrote it, but note there's some prefactors. There's some tensor here, and that tensor is just governed by two things. It's an integral over the Fermi surfaces of the Fermi velocity and the orbital moment of block electrons, which is another thing that should be in textbooks, because that would have saved us 6 months and some grief. But let me tell you what that is in a second. So this is just a sketch of what I'm going to cover in the next couple of slides. But what I'm trying to say is, at linear response, while semimetals are not very interesting as far as I can tell, because the only effect that I think was claimed to possibly be interesting, which was this linear response countermagnetic effect, is actually, first of all, it's an old effect, it's optical rotation, and second of all, it doesn't come from wild physics or topology, it comes from the orbital moment of the electrons, and you can get it out of semi-classics in a couple of lines. And just to make the case, we have 8 pages of supplemental material with the full quantum calculation, and I will spare you that. But here's a simple example of how topology makes things vanish that you might not have expected, and in particular, why, if you wanted just a simple semi-classical picture of why this effect comes out to be 0, here it is. So suppose you took the semi-classical equations of motion I wrote down before, and now I've switched what was called F is now called omega, because that's what sometimes gets used in this field. Little f is just the distribution function of the electrons. So this is kind of semi-classical transport theory in a magnetic field and with Berry phases. So this is the omega is the Berry phase, v is just the group velocity. And if you compute carefully, you see that there are actually 3 terms in the response to a magnetic field at linear order in the B field. There's one which is like Berry curvature along z, group velocity along z. Then there's Berry curvature along x, group velocity along x, Berry curvature along y, group velocity along y. So 3 terms. And at first glance, it's not obvious what they'll add up to, and I can give you a quick argument that this is actually 0 for any band structure. So even though this doesn't look all that topological because it combines something geometric, which is the Berry curvature, with the group velocity, which is not topological or geometric, those actually add up to 0, and that's why this thing vanishes.
Sorry, Joe.
Yeah.
Comment. So it's clear why Bz contributes to current along z, but how velocity along x contributes to current.
Yes, because there's a subtle term that often gets forgotten, which is when you do semi-classics, the phase space volume changes by a factor which is like 1 plus omega dot b. So there's an extra term that is sometimes not written down in semi-classics, but it is there. And that
Berry curvature here?
Yeah, that's right. 1 plus f dot b if you prefer. So there's an extra appearance, and when you expand that denominator to linear order, that gives you the other parts. So yeah, so it's a little subtle. I mean, I can definitely understand how, and if you miss any one of these terms, you won't get the right answer. But trust me that if you expand the semi-classical equations properly to linear order in B, then all 3 of these are there. And that's a good thing, because once you've got all 3, so we're looking at integral over all the occupied states of Berry curvature dot group velocity. The magic is just that one of these things is a curl and the other is a gradient, which means if you didn't have any monopoles, you'd get 0. If you did have monopoles, you have to be a little bit more careful, but it's still 0. And this was actually, we worked it out, and then we were slightly disappointed to find that Xiao Niu had already done it a year or 2 earlier. Somehow seemed to have lost that reference. So that was all semi-classics. This is the first page of the 8 pages of supplemental materials. So Kubo formula, lots of manipulation of derivatives and so on. If you really liked TKNN, that Thalassol paper I mentioned, then you'll like the supplement, otherwise probably not. But now comes the non-zero effect. So that was all saying, this is the semi-classical reason why you get 0, and that you can reproduce that and do the quantum mechanical version, and you get exactly the same identity, just with a lot more work. So to get something non-zero, you have to switch the order of limits. It's just like going from compressibility to conductivity. So the same thing happens with the magnetic field, and we can calculate the Magneto Conductivity if you want, where that means just only magnetic field. But a magnetic field at non-zero omega doesn't really exist once you have gauge invariance. There has to be electric field as well. You can't have the purely magnetic case. And so what this is really describing is the low frequency response to an electromagnetic wave. So you can what is that response? What controls it? And again, you can do some complicated quantum calculation, but the physics is very simple. If you ask about the optical rotation of a low frequency wave, it comes dominantly from the magnetic part of the wave, and it's because that magnetic field couples to the orbital moment of Bloch electrons, which is another emission may be an Ashcroft-Murray. So that's, this is the orbital moment of block electrons. I never thought about electrons in a crystal as having a rotational part, which gives you a moment, but they do. And it modifies the group velocity, the standard velocity term. So that gives me this extra m dot b term, and that solves the, that's how you get the semi-classical derivation of the formula I told you a moment ago. So this orbital moment should modify anything in the magnetic field. I said that a bit quickly. It's just saying that if I have a magnetic field, and if I believe my block electrons have an orbital moment, then there's an extra term in the group velocity that I should include, and this is the key to optical rotation in any material at low frequency.
So is that term, does that term come from that, like the phase space volume?
This one does not. This one is just simpler. It's just saying that when I think about E sub k, what energy should I use here? Well, in the magnetic field, I should use this energy, and this term only matters. It gives me an extra contribution to the gradient if the orbital moment depends on k. But generically, the orbital moment does depend on k, because these things, these are some properties of the wave function. Actually, the orbital moment is just like the Berry curvature, except that inside I put a factor of energy. So if I got rid of this h minus En, it would be the ordinary Berry curvature. So that's saying that at low frequency, I would have thought that only the Berry curvature could appear, but actually the orbital moment can appear as well, and here it does. So that's how it comes up. And then this is what I wrote before. So beyond linear response, there are lots of other effects, and I'm going to tell you quickly about one, but this is the only linear response effect in this predominantly magnetic limit. All right, so I want to say a little bit about nonlinear effects in metals, and then a little bit about hydrodynamics, and both of those are like, if you want, 2 5 to 7 minute talks, and I'm going to do them more with pictures than with actual calculations, I promise. So if you want to summarize, what I've just tried to convince you with some details was that if I look at the linear response to A of Q omega, then it's not very quantized. If I have Weil nodes, I get a nice simple formula because there aren't that many parameters in Weils, but it does involve the energy difference. It's not topological in the sense of only involving the topological charge of the Weil nodes. So I should look for something else. So this is not quantized, and now let's go back to optics, but let's think about non-zero frequency, and the effect I'm going to talk about is very analogous to this, which I think is one of the cutest experiments in graphene, even if it may not be as deep as a lot of the other measurements in graphene, but when I heard this, I thought this was cool, and I think it's the shortest paper in science that I've ever seen, which is, if you take a sheet of graphene and ask how much light gets through, say invisible. One reason why you can see sheets of graphene is that the answer is that one layer blocks about 2.3% of light, and that number 2.3% is pi times the fine structure constant, pi times e squared over hc. So this is a metal, and this is finite frequency, and it's not perfect quantization. As far as I know, this isn't protected interactions or something, but at least much better than an ordinary order of magnitude or something. This is roughly the right amount for how much does one sheet of graphene block light. So that shows you can get quantization in a semimetal of something. So what about these new Weil semimetals? What could be quantized? Should we look for something? And here, this is the relatively new, the second newest part of the talk. Everything I told you before about the circular photogalvanic effect was semi-classical. You can redo this derivation with quantum mechanics and prove what we had done in 2010 semi-classically. But let's go to non-zero frequency. So this is just spelling out in words the kind of pictorial argument I gave before. So we think that the original effect that was seen in these old experiments by Ganichev et al., and the paper that extended what we did to 3 dimensions and formalized it in various other ways is this nice PRB by Liang and Inti. But this is all the semi-classical effect. So we can derive it quantum mechanically, but it is ultimately low frequency, standard semi-classic, so you can get it out of the equations that I wrote down earlier. It's a pretty weak effect, sort of picoamp photocurrents for typical intensities. So here's how you get a quantized effect out of that. If you go to finite frequency, and you have a material, which unfortunately we don't have a very good sample yet, that I know of, we meaning the community, but if we got a sample that had positive and negative Weil nodes with some energy splitting between them. So in other words, the total Weil charge at one energy doesn't have to cancel. We want to find Weil materials with low symmetry so that there's some splitting like this. Then the following happens. You get what's called polyblocking, where at this frequency omega, there are no transitions across the Weil node down here. There are the sort of semi-classical effects here, but those are weak. they're dominated by a factor of 100 to 1,000 by the following calculation that I'm going to tell you the answer for, which is if I've just got one while node and I look at these interband transitions that cross the while nodes, this is purely non-zero frequency, doesn't have any low frequency analog, it's not semi-classical. Something magic comes out when you use the nonlinear optical formulas from John Sipe and collaborators to compute that, which is the following. The current you inject is quantized, and it's got a quantum which is e cubed over h squared. So the standard quantum we see a lot is e squared over h. Sometimes we see e over h. Just by units, the quantum here has to be e cubed over h squared, and that's what comes out of the calculation. And nothing else about the material comes out, at least assuming I've got a thin film. So if I don't attenuate in the material, then I just get intensity times Weyl charge times this fundamental, nonlinear optical scale. What the left-hand side means is this is the rate of current that I inject for right circular minus left circular. And more precisely, right circular and left circular will have a piece that is in opposite directions. So that's what we hope someone will measure. And it's important to say that this will be like the graphene case at best. It's not going to be 1 part in a billion like the quantum Hall calculation. But it would be, as far as I know, the first quantized nonlinear optical effect, and it would have a nice neat quantum. So I hope that someone is motivated. Now that people are actually measuring the CPGE in some Weyl materials, if we could find a better Weyl material and measure this, I hope that that's at least the scale of what you measure. So that's the quantum for this nonlinear optical effect, the circular photogalvanic effect. So that's what I wanted to, that's kind of the punchline about electromagnetic responses, and I can summarize it with a no and a yes. In linear response, there is no chiral magnetic effect, but there is optical rotation, which is kind of interesting. It involves the orbital moment of the block electron, but I wouldn't call it topological. Out of equilibrium, there are various things that happen, and there is this quantized chiral photogalvanic effect. And then that's the main part of the talk. If it's okay, can I take, so it's 5 now, can I take 5 minutes more to sketch the 2? Oh boy, 2 stuff. All right, I'll show pictures of it. Hydrodynamics of electrons. So I wanted to talk about this because this center happens to have a bunch of people who have done, it's kind of the leading place for imaging how electrons move around and also how electrons behave like fluids. So if you want something that's very in vogue for your generation is that normally we think about electrons as independent objects that scatter in dirty materials. If I've got a very clean material, it might be better to think about electrons as a fluid rather than as independently scattering quasi-particles. And there are various ways. This is from a Stanford experiment. These are different limits in which something about how electrons flow can be measured. And what we'd like is a system where you get interesting nonlinear hydrodynamical effects from electrons. So I have one picture, and then I'll have to do the words quickly, which is there's a class of one-dimensional problems where we can solve exactly the hydrodynamics. In other words, if you give me local equilibrium, I can evolve that toward global equilibrium with a funny kind of hydrodynamical equation. And this is to convince you, so blue and gold are the Berkeley colors. Blue is the hydrodynamical prediction. So blue, if you want, is an analytic theory. You still have to use a computer to compute it, but that's something that certainly you would think is approximate and has no chance to be exact. Yellow is an exact calculation from density matrix renormalization group. The particular problem is a certain kind of interacting spin chain, but the main point to make is this is an interacting many-body thermodynamic limit problem in one dimension, and yet we can exactly compute the time evolution of various problems. So if you're an expert, this works for some models in one dimension that we know are very special. They're what's called integrable. So even with interactions, I don't get chaos. But for a long time, the way to treat these models was actually discovered by Hans Bethe when he was a graduate student. I think it was 1931 or so. After about 40 years, C.N. Yang and his brother realized how to treat finite temperature. And now the community has realized in the last year or so how to treat dynamics, at least hydrodynamics. And I'm going to take one more minute to sketch how it's different from normal hydrodynamics. Normal hydrodynamics, there are 3 equations, if you remember your hydrodynamics. And there are 3 equations because there are 3 conserved quantities, which are particle number, momentum, and energy. Now, in these integral models, there are an infinite number of conserved quantities. So at first glance, you have to solve an infinite number of equations. It turns out you don't. You have to solve one equation. And I'm going to skip over why you just have to solve one equation and tell you what the equation is. So basically, you have to solve one equation because even though there are an infinite number of charges, you could view them just as different moments, as somehow simply related to one thing which is like a momentum distribution. It's the exact same thing that we write the Boltzmann equation in terms of for kinetic theory. So there's a magic kind of kinetic theory for integral models, which is the Bethe-Boltzmann equation. And it looks like a Boltzmann equation with two changes. One is there are no collisions. The Boltzmann equation is a lot easier if there are no collisions because there's no increase of entropy, there's no dissipation, and so on. So that's the good news. The bad news, but the bad news has a simple physical reason, is that normally there's the so-called streaming term, which is that particles move in between collisions with the velocity. What happens in integral models, so now I've got some infinite number of particles that are bouncing off each other. The velocity of the particle with momentum k at some point in space depends on the density at all the other momenta at the same point in space. And that's because the way integral models work, the reason why there are no collisions is that particles in an integral model, they pass through each other with a quantum mechanical phase shift. If you want a picture of that, it's like a little delay. So two particles pass through each other, they interact, which causes them to wait for a bit, but they don't lose their identity, they don't randomize their momentum, so it's a very restricted kind of collision. And this velocity we can calculate from the Bethe ansatz, from what are the phase shifts of all the different particles. So I'm not telling you what V is, and it's fairly complicated, but this is the equation we solve. And the reason why I wanted to mention this here is that all the people who measure beautiful electron flows, if you can do anything time-dependent, if you can give us a time-dependent evolution of densities in 1D, now we actually have a tool to predict it that we didn't have a year ago. And this is mostly useful for atomic physics, but I would love to see it used for electrons because electrons are my first love. And that's probably good enough to end on. So this is to summarize the last part of the talk, was just normal fluids and integral fluids both have hydrodynamics. The only difference is that integral fluids, the hydrodynamics is in some ways simpler actually. You can solve it with this one equation, and that is a bit of a surprise for people who have worked in this community for a while. So thank you for your attention.
Next question?
You promised to connect the wild semimetal and story.
Yeah, so they both, basically optical rotation, which is what we were interested in the cuprates, is the point, the connection is that it's actually the same quantity as the transport limit of the chiral magnetic effect, which people from the wild community have kind of been thinking about. So we had been working on a theory of optical rotation motivated by the cuprates. And people were talking about the chiral magnetic effect, but the connection is what I have in words here, which is that what people had realized for the chiral magnetic effect was that it couldn't be there at zero frequency. You had to have time-dependent magnetic field. And the connection is time-dependent magnetic field means electromagnetic wave. So the time-dependent limit of the chiral magnetic effect is exactly the optical rotation problem, and the optical rotation problem is what we cared about for kind of detailed reasons related to the cuprates. So they're connected theoretically. I mean, experimentally, I don't think they have. I guess the point is the chiral magnetic effect doesn't have any meaning in linear response except for optical rotation, and this is the formula. So as an example of why we wanted to rename it gyrotropic magnetic effect, people originally discussed it as a scalar. The topological thing that had been talked about, this would just be a number, but it's actually a tensor. You know, in general, if you've got some low symmetry crystal, the orbital moments will point in all different directions, but this is the formula that I want someone to go and measure. And it should actually be there in selenium. You know, anything that is a semimetal that allows optical rotation and that you can measure at low frequency, this should be the effect. So I guess that's it.
So you're talking here about rotation and transmission. This is
Yes.
not, so this
Exactly.
has nothing to do with reflection.
Exactly. So we were.
I
Yeah.
thought you were going to answer. You were motivated.
We were motivated by exactly.
the reflection experiment, but you're not trying to explain it.
Exactly. I don't understand that. That's the main point I'm making. But if you want, yeah, we were motivated to do this because when we were worried that our theory would not vanish in reflection, and then we realized we basically had to derive. The reason why we derived this identity was if this was not true, aside from there being a chiral magnetic effect, if this was not true, we'd have had a Kerr effect in a time reversal invariant system, which we know is impossible. So we were satisfied when we got that, but then in the process, the spin-off of that theory is this formula. Yeah. So it's motivation.
Second question, I got to look. To get Weyl points with different energies, you need a magnetic field, right?
No. You
have to break time reversal symmetry somehow.
You not quite. You can't have any mirrors, but you can't have any mirrors that act non-trivially on the K vectors. But an example, strontium silicide is a non-magnetic material that is a material that has time reversal symmetry. It breaks inversion. So for example, something that's allowed by time reversal would be to have two positive Weil charges at one energy and two negative Weil charges at a different energy. Because time reversal will take the plus charge to the plus charge.
Okay, one last question.
I just want to confirm this curve effect is zero only for normal incidents, right? If you have optical incidents, then you can't have that for inversion broken systems.
That's right. That's right. So off normal incidents, the symmetry requirements are much less strict, and almost anything will have it. But you would think the point of this carefully designed. So, for example, I have a colleague, Joe Ornstein, who is an optics expert and by nature a tiny bit skeptical. He was Professor Kalik's thesis advisor, and he spent a long time trying to ask bothersome questions of the Stanford people about maybe their experiment's not normal incidents, maybe there's some optical element off, and in the end he was satisfied.
So you don't need normal incidents. It's, with the Sagnac, it could be any incident you want, but it has to come back.
Exactly. The part that you're interfering with.
What you're looking at interfering things that are going through the same optical fibers in the same directions,
Yes.
so that whatever is reflected is coming back into the same direction that it started from.
That's a better way to put it. Yeah.
Okay, well, let's thank Joel again. Oh, that's nice. I'm going
Yeah. Well, great. Well, thanks, Senna. Yeah, I tried to pack a lot in because there are a lot of experts here, but I appreciate it.
Oh, yeah.